All right, let's look at a more difficult waveform to approach to compute the Fourier series coefficients. So the waveform on top x of t is similar to some ones we have in the homework, where what I have is, in this case, if I look at this and I try to identify the period, I see that t equals 4. That's the time period over which this thing repeats. So that's the first step, is always to identify what the period is. And then I need to figure out what the alpha n are. And I use the basic formula right here to figure out my alpha n. Now, the one catch is that alpha 0 is just the average value of the waveform over a period. So we'll have to remember that. But the thing that I see here is when I define what the function x of t is, if I define it over a period, I see that essentially what it looks like is that over part of the period, I have a flat line that's x equal to 2. And then for part of the period, it looks like I have a line that's falling off. And the way I can think about this is it's like this waveform x of t is equal to the sum of two other waveforms, x1 of t and x2 of t. This is an easier way to try to approach the problem. So notice what I've done is I've said that this sort of box waveform here plus this triangle waveform here, if I add those two together, then I get the waveform on top. So if I do that, what I can do is I can say, well, let's figure out what the alpha n1 coefficients are for this waveform. Let's figure out what the alpha n2 coefficients are for this waveform. And we can add them together to get the coefficients for this one. Because if we think about the way you would get the alpha n, right? Alpha n is equal to 1 over t. And again, I can choose whatever time period I want to integrate over. I'm going to say I want to integrate from 0 to 4. That's one period. And of x of t e to the negative j n omega naught t dt. I see that that's equal to 1 over t times the integral of 0 to 2 of x1 of t e to the negative j and omega naught t dt. So in other words, if I took this waveform here and did that integral, plus if I did the integral, the one on the bottom, that would be 1 over t integral from 2 to 3 of x2 of t times e to the negative j and omega naught t dt. Okay, so if I look at that, these look very similar to sort of coefficient equations. So I'm going to call this alpha n1, and I'm going to call this alpha n2. And then what I see from this result is that if I wanted to compute alpha n, one way I could do it is to add those two sets of coefficients together. This is a way to make my math make a lot easier when you put it into MATLAB. And it's a way that'll help you to know that your answers are correct. Because what I'm going to do is I'm going to compute the alpha n1, and then I'm going to try to reconstruct the waveform in MATLAB to see if it looks like this x1 of t. Then I'm going to do the same thing with the alpha n2. I'm going to compute those and see if the waveform I recreate looks like this one down here, this x2 of t. Then I know if I add them together, then it should look exactly like x of t up here, right? That's the thing that'll help me to do this. If you think about it, throwing all of that information in the MATLAB for x of t, it's really hard to sort of debug and figure out where your problems might be coming in if you get these really complicated expressions. So I'm going to try to reconstruct x1, then reconstruct x2, and then I know I'm right for x of t when I add them together. Okay. All right, so let's take that approach. All right, so first thing I want to do is figure out, well, what is x2 of t over the time period I'm integrating over? So from 2 to 3, how do I express that waveform? Well, based on my original picture here, I saw this guy has a height. All right, has a height of 2. Right, so this guy has a height of 2. If I can get it to do that. So the height here is 2. I'll write it there. So this guy starts at 2 and he drops to 0 by 3. So that tells me that x2 of t is a function that's linear with a slope of -2 because he dropped 2 in a distance of 1. So -2t plus some unknown y-intercept b. And I know that x2 of t, if I look at it, is equal to 0 at t equal to 3. So x2 of 3 is equal to 0 when t is equal to 3. So b must be equal to 6. So I know that this function is -2t plus 6. So we'll go ahead and do those two integrals. So x1 is equal to a value of 2 from 0 to 2. So here we go. Let's start the integral. Alpha n1 is 1 over t integral 0 to 2. x1 of t, we said, is the number 2. E to the negative j n omega naught t dt. If you don't see that, you can go back to the top to review it. Now what I'm going to do in this problem is I'm going to say, let's let a, I'm going to make a substitution and say a equals negative j n omega naught. And I'm going to write this as 1 over t integral 0 to 2 e to the a t. So if I carry this integral through, it's 2 over a t times e to the a little t evaluated from 0 to 2. So that becomes 2 over a t times e to the 2a minus 1. All right, so with that, we have our first result. Okay, by making this substitution here, we make everything very clean. Then I have to do this integral to figure out alpha n2. Well, that's the integral from 2 to 3 of x2 of t. All right, so now I'm going to write that as alpha n2 equals 1 over t integral from 2 to 3. And it's 6 minus 2t. That was the function that we found over here, 6 minus 2t, times e to the negative j n omega naught t dt. Now, again, I'm going to make the substitution here that a equals j n omega naught. So I'm going to evaluate the integral. All right, but before I evaluate it, I'll plug in the a value. So this becomes integral 2 to 3, 6 minus 2t e to the a t dt. Now, this is going to require a u substitution. So the way I look at this is the rule that I learned, LIPET. This is an acronym that I learned to figure out how to make the u substitution. So I look for the function that is whatever these functions come first, I make it the u substitution. So it's log, inverse trig, polynomial, exponential trig. So I have a polynomial and an exponential. So the polynomial becomes my u substitution. So I have 6 minus 2t is my u substitution. That means that du equals minus 2 dt. dv equals e to the at. So v would be 1 over a e to the at. All right, now, the thing to remember is that because this thing was, remember the integration by parts is udv equals uv minus integral of v du, like that. So the way I would write this is I would say 1 over t times the result that I have here. So u is 6 minus 2t, all right, times dv, so times v. So v is 1 over a e to the at. And this is evaluated from 2 to 3. We got to remember that because this was a definite integral. So it's evaluated from 2 to 3. Okay. And then I have the other piece here, minus u, or minus integral of v du. So v is 1 over a e to the at. du is minus 2 dt, so this becomes plus 2 over a times the integral e to the at dt. That whole thing evaluated from 2 to 3. Okay, so I gotta keep going here with this whole thing. This is where it gets pretty ugly, but notice making a substitution like a equals negative j n omega naught makes this a lot cleaner. All right, so I have 1 over t times the integral 6 minus 2t. And I'm gonna actually, what I'm gonna do is I'm gonna start evaluating this term right here. So I'm gonna evaluate it first at t equal to 3. So one thing I noticed right off the bat is 6 minus 2 times 3 is 0. So actually, for the limit at t equal to 3, this first term goes away. So I have just the second term, right? Just if you're not clear on that, let me just not skip that step. I'll say 6 minus 2 times 3 times 1 over a e to the 3a. This term goes to 0, minus 6 minus 2 times 2, so 6 minus 4 times 1 over a times e to the 2a. Okay, that's the first part of the integral. Then I have the second part of the integral over here, which becomes 2 over a squared times e to the at evaluated from 2 to 3, again like that, right? I brought an a down when I did this integral, so I have an a squared. So this whole thing now becomes minus 2 over a t, so I'm carrying the t through now, times e to the 2a plus 2 over a squared t e to the 3a minus e to the 4a. That is my final answer, where I have to remember that a equals negative j n omega naught. Okay, so that is now my final answer that I need to plug in to MATLAB. So I have my alpha n2. So that's the thing to remember. This was alpha n2. There's also an alpha n1, and I can add these together. Now, one thing I probably should note real quick, and you'll notice that technically, if I look at both my alpha n2 and my alpha n1, I have here, since a is equal to negative j n omega naught, if n is equal to 0, I'm going to have a 1 over j omega naught times 0 in all of my terms in alpha n and alpha n2. That's problematic. So what I have to do is I also have to do the DC term, okay? The DC term in each of these waveforms is given by this guy. So calculating the DC terms is pretty easy, because the DC term is, the meaning of this is the integral over a period, right, times 1 over t. So the integral over a period is just the area under the curve. So this is pretty straightforward. If x1 has a height of 2 and a width of 2, and it's just a box, the area is 2 times 2, right? So alpha n, or alpha, I guess I'll call it alpha 0, 1, because it's for n equal to 0, is 1 over t times 2 times 2. Okay, so that's important, because it's just width times height, all right, is the area of that rectangle, and it's times 1 over t because of the 1 over t here. If I think about the same thing for the triangle, it becomes 1 over t times 1/2 the base times the height. So the base is 1 and the height is 2. Okay, so those are the average values of the two waveforms. And I can just say that alpha 0 is equal to alpha 0, 1 plus alpha 0, 2. And I would see that for all the reasons that I derived right there. Now, I want to know those numbers separately rather than just using the approach I'm going to use here and letting n be a variable, because when n equals 0, these formulas would be really problematic down here. That would cause a problem. So I have my special values here. And then for all other values of n, I have the two formulas that I got to here and here at the bottom. All right, so let's look at how I put that into MATLAB code. All right, so I'll put this here, and I'll put my MATLAB code here, okay? All right, so let's take a look at how I coded this in. So to start out with, I clear all, I set my period, I define omega naught, I created a vector alpha n, then alpha n1, and then alpha n2, and I'm going to do this for 100 harmonics. So I create an n vector that goes from -100 in steps of 1 to 100. And then I'm ultimately going to plot x1 and x2. So I make vectors that are full of zeros for both x1, x2, and x. Now notice then what I do is I have two for loops ultimately. My first for loop is where I fill up the alpha vectors. My second for loop is where I actually create the waveforms. So here in the first for loop, what I have is I'm looping through all the values of n. And when n equals 0, what I'm doing is I'm using my formulas up here. All right, so I created this intermediate variable value 1. Value 1 is essentially the value over here of alpha 0, 1. It's the DC value of x1. So notice what I did, 1 over t times 2 times 2, exactly what I have right here. All right, for alpha 0, 2, right? I called that val2. Val2 is 1 over t times a half times 2 times 1, exactly what I have over here. And then alpha 0 was alpha 0, 1 plus alpha 0, 2. I just added those two together. All right, now notice what I'm doing here on this line. This line, I'm just appending value 1 to the end of the alpha n1 vector. This line right here, I'm appending value 2 to the end of the alpha n2 vector. And then for my alpha n, I'm just appending the sum val onto the end of the alpha n vector. Okay, now where it gets trickier is when I come over here and I try to look at alpha n1. So val1 is what I call alpha n1. And notice what I did here. At the beginning of this statement, I defined a equals -j times n. And specifically, I said n of k, because remember, n is a vector for me. And so n of k is a specific value of n. Okay. And so I do -j times n of k times omega 0. Then what I do is I say val1, right? This is my alpha 1 value. So I use this formula that I have over here, right? 2 over a times t times exponential of a times 2 minus 1, okay? And then value 2 is my alpha 2 value. All right, so that ended up here. And just to be clear, I noticed that I wrote, this should have been alpha 3a minus alpha 2a. Somehow I got a 4 in there, right? So I went from, so e to the at, right? This was evaluated from 2 to 3. So that should be e to the 3a minus e to the 2a. So I wrote that wrong. All right, it's my alpha 2 value. So let's see what I wrote in here. I have minus 1 over at times 2 times exponential 2a. That's this term right here. Remember, I'm always trying to match up these terms like that. Over here, I have 2 over a squared times t times exponential 3a minus exponential 2a. And then val equals val 1 plus val 2. And then I just do the appending that I did before. All right, at that point, that's the way to build this up. The really useful thing for me is to make this definition at the beginning, which makes all of this math look a lot cleaner than it would have otherwise. Trust me, putting all this onto one line with the j, n, omega naughts and everything would have made everything really, really tricky. I also, by having this negative sign in here, it means that all of the sign cancellations and stuff that would have been in the math otherwise which would have caused a lot of mistakes for me, is kind of covered up. All right. So then what I have down here is where I'm actually reconstructing the waveform, right? So whatever, as I loop through the values of n, I take my existing x1 and I add to it alpha n times exponential j n omega naught t. Same thing for x2, same thing for x. All right, now what I want to do is I want to just plot for now for myself the first waveform. And if this works, what I should see is, what I have here. All right. So what I have here, so x1 should just be a square wave that goes from 0 to 2 with a height of 2. And then it's 0. And then at t equal to 4, it should go up to 2 again. And then at t equal to 6, it should drop. Let's look to see what this guy looks like if we run it. So I run that. I'll get my figure 1. And boom, there it is, right? So I've got something that t, as based on the way I've drawn this, right? So looking at my t vector, I did it from negative t to t, which means I did it from -4 to 4, right? So that's exactly what I have here. From -4 to -2, this guy has a height of 2. And then from 0 to 2, he has a height of 2. That's exactly what I had in my image over here. Now it still has these little ears, but we said that's always something that happens with the Fourier series. Now, what I want to do is now I want to look at x2. So I plot x2. I don't have to rerun the whole code because it was already there. So let's just run that section. And there it updates. So now if I compare that to this graph, it looks like I had a triangle with a height of 2 between, so it starts at 2, between -2 and 1. So between -2 and -1, I see this guy has a height of 2, drops to 0, right? And then in the next period, at t equal to 2, it should jump up to 2 and then drop down to 0 by 3. That's exactly what I have here. At t equal to 2, this guy jumps to 2 and then comes down. So it looks like I've got exactly what I would expect. So now if I look at x, and again, I don't need to rerun the whole code because I already did. Run that, and boom, that looks exactly like what I have in this picture, right? So at t equal to -4, jumps up to 2, stays flat, and then at t equal to -2, it drops off, just like it does here, and then at t equal to 0, jumps up to 2, stays flat to t equal to 2, and then it ramps down to 0 at t equal to 3. So this is an easier way to try this. And again, there's a number of simplifications that I made here. So hopefully this will help you to kind of think through some of those more complicated integrals.